I think we're going to use some of that grant to help us set up our podcast capability. And then also we're supported by the local humanist group, the Prairie State Humanists, which is a humanist group west of Chicago. You're welcome to check out our Meetup page, meetup.com. And then once you're on Meetup, you can look for Prairie State Humanists and find our upcoming events. We do a lot more than just sidewalk science. The news that we have is that on August 12th, which is a Thursday, about 2 months from now, we will be joining a conversation with the American Humanist Association via one of their educational Zoom broadcasts. And we're going to be talking about a very timely topic, UFOs.
But I don't know how to identify them.
I don't know how to identify them either. It could be we have not a lot to talk about, so we'll see how it goes.
Conversation.
Yeah. So we're going to do that August 12th, but between now and then, we'll have more of these regular Sidewalk Science programs. So let's go ahead and get started. As I said, we're going to start with a little bit of science news. Joanne, you had a couple things you were telling me about right when we were getting started or before.
Yeah, just an interesting article. And again, all of our physicists will probably want to talk about this. There's been recently, they looked at the LIGO information about the two black holes that came together, and they appeared to confirm Stephen Hawking thought that essentially they're additive. So two black holes came together and made one black hole that was twice as big.
And parts didn't break off.
Parts didn't break off.
Yeah.
It sort of hung around there. And again, Stephen Hawking appears to have made another interesting prediction that probably represents reality.
So Dave, our technical director, who's the man upstairs, says that our audio is being doubled on the YouTube. Not sure why. Maybe if you're not talking, can I ask you to please mute yourself on the Zoom meeting? Maybe we're getting a feedback from a microphone or something. I'm not sure. Let me just type at Dave for a second.
This is which microphone are we using?
So we're using the microphone, pardon us, we've only been at this a year, so yeah. You know how it goes with, yeah, it's just the select a microphone. Yeah, it's the microphone on the webcam actually is the one that's being used right now, which has proved successful in the past. So hopefully Dave can work out the audio issues,
the glitch,
the echo. What if we talk with an echo?
Yeah,
everybody confused. All right, so science news. So anyway, Stephen Hawking predicted that when black holes consume anything up to and including another black hole, that their surface area will not diminish, and their surface area. It's kind of a strange concept. I think John and Ivan, maybe theoreticians conversant with general relativity, can tell us that it's kind of a weird concept because space is kind of stretched radially in a black hole, but whatever the case, the total surface area of the black hole does not diminish. That's the Hawking rule, I think.
Look at them all jumping in on this.
Yeah.
I want to jump in and say I don't know anything about this.
Yeah, there you go. Neither do I.
Hawking pointed out that there's an analogy between thermodynamics and the area of the black hole horizon, and in particular that the black hole horizon represents entropy, and the same equations that we use in thermodynamics seem to predict what goes on with the black hole horizon. And he did this before his discovery of Hawking radiation, where he then came up with a temperature. And so, yeah, there is some intimate connection between gravity and thermodynamics that really still isn't understood.
But about the area of a black hole, So when two black holes merge, as in the LIGO events, and there has been several of them, then the mass of the two black holes, of the combined black hole, is a bit less than the mass of the two individual black holes. The difference is radiated away in gravitational waves. And the surface area of the combined black hole is bigger because it's more massive. However, also Hawking said that black holes will evaporate eventually if they've got lower temperature than the microwave background temperature they're embedded in. When they do so, they get hotter and hotter, radiate away, and eventually disappear or become a singularity. Now that radiation away is not increasing, it is increasing entropy because it's radiating all these photons, which are entropy. So as John says, the entropy is increased, but on the other hand, that's the entropy of the whole system, including the radiation, right? The entropy of the black hole itself will disappear as the black hole disappears. Now, whether it actually disappears completely or down to some crazy singularity is still up for grabs, I think.
Oh, it gets much stranger than that when you realize that the actual formation of the horizon in external time is infinitely far in the future because of the gravitational redshift. On the other hand, the radiation theory predicts that the black hole will evaporate in finite time.
Yes.
And nobody has quite squared that circle.
Oh, I was at a meeting at Fermilab about a year and a half ago now. And I don't remember which one of the noted persons it was that was speaking at the time, but he had calculated that it would take 10 to the 76 years for a black hole to evaporate.
Like a stellar mass black hole?
Yeah, stellar mass, well,
Yeah,
a black hole, because the larger they are, the faster they go and so forth.
The slower they go, the larger they are.
And so,
any black hole that's evaporating now has to have and losing mass, has to have a temperature less than the 2.7 degree Kelvin that it's sitting in. And that means its mass has to be less than something like, I don't know, it's 100 kilograms or 2 tons or something like that.
You went through a very long and involved calculation and came up with 10 to the 76 years. And that's the number that's stuck in my brain. And then I look at, what is 10 to the 76 years? Well, we've been at 13.4.
We're about 10 to the 10, 10 to the 11. Yeah.
Now, so take 10 to the 76 and take 10 to the 11th away. Well, and then take another 10 to the 11th away. And then 10 to the 76 is a very, very, very long time in the future.
We might collapse down to a big crunch before then. I don't know.
I don't think I'll see it.
No.
So you had another news story about
Archaeology.
okay.
There's a brand new discovery of a rhinoceros. Now, old rhinoceroses are not the same as new rhinoceroses. This sort of looked like a horse,
Okay.
except it stood 16 feet tall at the shoulder and weighed 20 tons.
Oh my goodness.
And and from what we can see, it's the largest land mammal ever on Earth. So it's not to say it's a dinosaur type, but still 20 tons is a very, very big creature. So we have a new record for mammals at 20 tons.
So that's something like Andre the Giant could finally ride a horse if he found that thing.
But 16 feet at the shoulder.
That is pretty big.
So the head is up there about 21, 22 feet.
Almost 2 basketball hoops just to the shoulder.
So you put a giraffe beside it, and the giraffe looks tiny.
Wow.
I mean, this is a big creature. So those are the 2 big ones that I came up with this week.
I think it's interesting that throughout the fossil record, evidence seems to indicate that the largest animals are herbivores.
Yes.
Not predators, not meat eaters. And I'm sure if Abby were here, she could talk to us a little more about why that is. It has to do probably with trophic levels and sustainable populations and whatnot.
Yeah, lots of food.
Yeah.
So Joanne, did that giant horse-like mammal become extinct when the dinosaurs did?
Oh no, this is a mammal, and it went extinct about 15 million years ago.
15 million.
15 million. So this is very recent in terms.
Very recent, yeah. Because the story was when the dinosaurs became extinct, the mammals were the size of shrews and so on, mice and so on.
Right.
They survived because they could they could bury themselves and stuff like that.
Two nits here. The first is that the dinosaurs didn't become extinct. There are more extant species of dinosaurs now than there are mammals. And about the same number of lineages of dinosaurs made it through the Cretaceous tertiary extinction. We just don't call them dinosaurs anymore. We call them birds.
Yeah, right.
But it wasn't like, oh, mammals took over from the dinosaurs. They're still around. And by some measures, they're more important than mammals.
Mhm.
The other interesting thing is the largest known creature ever to live is not an herbivore. It's the blue whale, and it eats tiny animals.
Oh, that's right.
So-
Thank you, John. Thanks for reminding us of that.
Yeah, so when I said dinosaurs became extinct, I mean, the giant ones did, but the little small ones survived, right? You agree with
Yes, the
Maybe-
giant ones did, and the little small giant dinosaurs and mammals of similar stature
Yeah.
survived.
Right.
And that's what we have around us now.
Oh, there was also an interesting one about T-Rex. It would appear that wherever T-Rex was, there were no other carnivores. It would
Wow.
appear that the young T-Rexes were very quick, very agile, and took over all the intermediate slots for carnivores. So when the T-Rex moved into the neighborhood, they were the only ones left. And until they got huge, then they would eat the big ones, and the little ones would eat the little ones, and so forth. So it was just, once T-Rex was there was no other carnivore.
Wow, I didn't see that. That's amazing. So they moved into the neighborhood and took over.
Took over completely.
That's amazing.
Peter has a waved hand.
Hey, Peter, what you got?
Hi, yes, with respect to the giant rhino,
Mm-hmm.
so to speak.
Yeah.
What is the genetic lineage of the giant rhino? Because if
no
in
idea.
fact there were these tiny amphibious and mammal and other creatures, one of them had to start that process, or X number of them, right, in order to become from the acorn to the tree being the rhino. Is that
Yeah.
correct?
Well, again, as we look at evolution, we see that evolution takes all sorts of interesting paths. And the only thing I could say about the rhinoceros is the one that they discovered is long ago, and I don't know if it's on the same branch as the modern rhinoceros. It may be on a slightly separate branch. So I think if you were really interested, you might want to look that up. The article was recently published, and you might look up all the lineage and heritage of the wonderful world of rhinoceros.
Yeah, and there's a link to whales too.
Fascinating.
Isn't what our whales are
Thank
from
you.
hippopotami, I think, not rhinoceri or rhinoceroses.
Rhinoceros.
Anyway, we need Abby here to help field
Abby,
some of
where
these
are you when we
questions.
need you?
It says rhinos. It's simpler just to say rhinos, okay?
Yeah,
Yeah,
it
but
is.
not as fun.
Hippos and rhinos.
One of the fascinating things is that these days, if you look up, categories of animals on Wikipedia, they give you their place in the tree of life, along with links to Wikipedia articles that carry you back hundreds of millions of years if you wish.
Yeah.
And you can get absolutely lost in this stuff. It's very fascinating.
It's like reading an encyclopedia. You just
Well, it is an encyclopedia, but this is better than an encyclopedia because you want to know, okay, here's the ancestor of these 5 groups. What was it like? And then you click on that link and it shows you, and then it's one of these 5 groups and it has this ancestor, and it's again, you can spend hours doing it. I do it sometimes.
And before you know, you've spent millions of years of research.
That's right. Wondering
how we're related to butterflies, right?
Yeah,
right.
That's right. If you can find that kind of stuff out now pretty easily.
It's amazing. It's just amazing.
The stuff that we used to spend days working through the stacks.
Yeah, I've got an Encyclopedia Britannica in my personal library that I haven't cracked open in probably 20 years. it's sad, you know, all the effort that went. I guess there's a lot of effort in Wikipedia too, for that matter, but it's amazing the information you can find. All right, we need to move on, be mindful of our time. We've got a deep dive topic for today, and we take turns at that. Today is Mike Albro's turn. And Mike, what do you have for us today?
Right. Well, I'm going to explain how we know so very little about the universe. In fact, we only know about 4 or 5% of it. The rest we don't know. So God, we don't know a lot. Right. Okay. So this is about the dark side. And can I share my screen? You can hear me okay, I guess.
Yeah, let me, I warned Dave earlier that there would be some, you'd have some slides. So let me make sure that he's ready for that.
I'm sharing my screen, and if I go full screen, maybe I can go full screen.
So hang on just a second. Let me make sure that Dave is got that up and ready to go before you launch into your discussion of it. Sorry for the sound of my typing that may be picked up by the microphone. Microphone's far enough away, it shouldn't be too bad. All right.
That's looking good.
All right. So until that, yeah, we've got the slides up on YouTube. We did have a slide, a chat question from AJ. Can a single species survive by itself? I don't, unless it's an autotroph that eats sunlight and nothing else, sunlight and rock. I don't know of any species that could possibly survive without, you know, food. So no, I don't know. And certainly it's hard to imagine a context in the ecosystems of Earth where a species would be isolated all by itself. So I don't think so.
The closest that I can come, and this is a maybe, the critters that live deep down inside of the Earth, that the kind of things that might make petroleum, oils, and that kind of thing, we really don't know much of anything about them. And that may be a unique environment, but obviously they're unique critters.
Yeah, chemotrophs are what those are called.
But boy, to go beyond that,
yeah, we don't. I guess we don't know. Again, we wish Abby were here, but it seems implausible that a species could be all alone by itself without other species. So, Mike, everything's ready. You want to go ahead?
You see the screen? You see the whole right side. My right side is covered up by pictures of you guys, but maybe you can see the whole screen. Anyway,
we can. Yes.
The topic for today is a dark side of the universe, and I'm a scientist at Fermilab. They don't pay me anymore. I'm retired, but I'm still doing this stuff. I got my PhD in Manchester back in '69, long time ago. I have 18 years at CERN, living there, and then I was professor at Stockholm University, and then came here 30 years ago to work at Fermilab, where I and my collaborators, many of us, discovered the top quark in '95. And I've been on the LHC, one of many thousands of physicists finding the Higgs boson in 2012. So now I'm actually still working, proposing a search for what we call portals to the dark side.
Ooh.
A gateway. The dark side is universe we don't know what it's made of, but it's there, and I'll explain it. So the story starts back in the 1930s with this gentleman called Fritz Zwicky, who was an astronomer, and he was studying galaxies. And this is a picture of a cluster of galaxies called the Coma cluster. It's in constellation of Coma Berenices, the hair of Berenices, cluster of about 1,000 galaxies. And actually, and what he did was he estimated the energy of these galaxies, of motion, kinetic energy, and also the potential well they were in from the masses of all the galaxies. And there's a theorem which I won't explain called the Virial Theorem, relating the kinetic energy of a set of objects to the gravitational potential energy that they're bound by. And he used that theorem basically saying that the galaxies are moving too fast to be held together by the gravity of all the galaxies together, unless there's a lot more mass than we can see in the stars of the galaxies. Of course, he didn't see the stars, but just estimating their numbers by the numbers of stars we have in our local galaxies and so on. So a lot of uncertainty in that, but he came out with a thing as conclusion that there's a lot more matter than we can see in stars. He didn't know so much about dust and gas and planets, but we'll talk about them. They don't contribute too much. And he came up with, he called it, should be dunkle Materie, or dark matter. He was Swiss, Swiss-German. And it really should be called invisible matter, because I think of something dark as something like a black thing that absorbs light. But in fact, it doesn't absorb light, it's just invisible. His estimate was that there are about 500 times more mass in this cluster of galaxies than there is in the stars. And he was much too much there. It's not 500, it's much less, but still, he got this started. And then it didn't progress until the next slide. Vera Rubin, you see a picture of her as a young astronomer there, working in the Lowell Observatory in Flagstaff, and with Henry Ford, who did a lot of the technical instrumentation and so on, in the many years of observation. But in about 1970, she published a paper in the Astrophysical Journal about the rotation of the Andromeda Nebula. So this is a picture of the Andromeda Nebula, which I hope you have all seen with your naked eye by going to a dark place and looking at a dark sky at dark night. You can see it, at least the bright part in the center. And what she did was measure the motion of the stars coming towards us and being therefore slightly blue shifted light, or away from us being red shifted. So on the left side or the right side, she could see they were coming and going, and calculating the rotation speed of this galaxy. I mean, it takes, I don't know, hundreds of millions of years to rotate once, but it's rotating. And from that, she could calculate the amount of matter inside as a function of the distance from the center. And that's the matter that has gravitational field. So stars, gas, dust do that, planets do that. Of course, they don't contribute very much. The mass of planets in the solar system is much less than the star. And then we now know there's a supermassive black hole in the center of the galaxy, which doesn't also contribute enough to account for this. She measured the rotational speed or velocity, and you see a more modern plot on the bottom left here. This is the speed of rotation of stars, and then at larger distances from the center of the galaxy in hydrogen gas, where you measure the spectral of the 21 centimeter hydrogen line. Now, what you expect from the mass we know about in stars is this curve that reaches a maximum speed, and then it tails off as you go further and further away from the mass in the center of the galaxy. But it didn't fall off. It keeps rising, as if there's more and more mass out in the outer suburbs of the galaxy, if you like, than we can see in stars and gas and dust. So a lot of work, many other galaxies were studied. And I think, here's a picture of her in later life, loving astronomy. And she gets more credit than anyone else, I think, for discovering dark matter. By the way, doing that while raising 4 children, who all went on to get PhDs in the hard sciences and maths. And also, by the way, Princeton rejected her application for graduate studies because they said we don't allow any women to come and do astronomy graduate studies. But she got other good jobs, of course. And so now, I mean, we know it's there. It's not 500 times more than the stars and gas, but it's about 5 times more mass. Is that particles yet to be discovered? Most physicists think it probably is. Could it be micro black holes or something else? Or maybe not even particles, but some sort of continuum somehow. But most physicists think it's particles yet to be discovered. So we're looking very hard. So Vera Rubin, this picture of her with John Glenn here. She got a long list of honors, but she didn't get the Nobel Prize, which I think was very unjust, especially as 3 men got it for discovering dark energy on much less solid ground than the dark matter. So there's something wrong with that. It just shows that Nobel Prizes are not always a good figure of merit about your ability to discover stuff. But she does get an observatory named in her honor. Here's a picture of it
It was called the Large Synoptic Survey Telescope. It's under construction in Chile on a mountaintop, and it's now the Vera Rubin Observatory. By the way, following in Hubble's footsteps, because he discovered, you know, the distance of the galaxies and how big the universe was, and he didn't get the Nobel Prize either. But he has a telescope named after him, as you know. Astronomy was apparently not considered physics then, so it wasn't considered worthy of the physics prize. That's a bit of history. So then the next step in the story is, or one more step, is the so-called bullet cluster. It's again clusters of galaxies. In this case, two clusters of galaxies that collided, or rather passed through each other, because galaxies are moving around, and so clusters of galaxies moving around. This was about 2008, this was announced. They measured the mass distribution by a thing called weak gravitational lensing. And they were, the top left plot shows contours of the mass as they've derived from this weak lensing. What is that weak lensing? Well, as you surely know, gravitational lensing was first predicted by Einstein and observed by Arthur Eddington in 1919 at a total eclipse of the sun, when he observed, you could see the stars in the background to the sun, and Eddington showed that there were images of the stars were shifted a bit outwards by the gravity of the sun bending light. And that made Einstein famous at that time. In this case, the whole mass of the galaxy cluster, the gravity of the cluster of galaxies is shifting and distorting images of background galaxies that are far, far away, much farther away than this cluster. So that's a very clever trick by studying the distortions of galaxies to measure the mapping out the masses. And on the right, you see a picture which is sort of fake color, but what you see here is the reddish light here is actually X-rays from hot gas that was sort of left behind when the two galaxies passed through each other. The gas was sort of semi-slowed down and heated and emit X-rays, which is plotted here as the red blobs. And the blue blobs is just reproducing the mass distribution derived from this gravitational blending. So this shows that when the two galaxies cluster pass through each other, there are like two components, one which was the gas and interacted with itself and slowed itself down and heated up. But the matter component, this dark matter in blue, went through. So it's very weakly interacting. It did not slow itself down by interacting with the other. So in this thing, we see dark matter seems to be very weakly interacting compared with gas. And we think it is weakly interacting. Now, could it be machos, massive compact halo objects, which could be black holes, neutron stars, very faint stars, white dwarfs, rogue planets, made of normal matter? Or could it be what we call WIMPs? We like these funny names, weakly interacting massive particles. And so here's something about black holes anyway, because black holes certainly contribute to the mass of the universe, but we don't think, well, so here's some great black hole pictures. I mean, this one you've seen on the left, it's a supermassive black hole at the center of this big galaxy M87, as imaged by the Event Horizon Telescope, which is a combination of telescopes covering half the hemisphere of the Earth, and so getting a very good resolution. And that picture of a black hole, actually what you see is the light bent around by the black hole's gravity. The black hole itself is much smaller than the black dot in the middle from that distance. And then the Nobel Prize last December was last year was given to a study of the black hole in the center of our galaxy in Sagittarius A star. Sagittarius is the constellation it's in, the direction of the center of the galaxy. And it's about 4 million suns. And what these astronomers did was they could actually see stars in the vicinity of the center of the galaxy. And over many years, like 15, 20 years, measure the movements of these stars and calculate the mass of an object in the middle, which they don't see, but they say it's got some mass. I didn't know, 500 million suns or some, 4 million suns, I say there. Anyway, there's new news because a paper came out just recently suggesting that this may not be a black hole in there, but a huge lump of dark matter. Okay, also very heavy. I mean, that would be even more strange and exotic and exciting than a black hole. Now black holes are becoming to a penny sort of thing. We don't know, but that would be very interesting. And on the right, I mentioned neutron stars, because neutron stars are collapsed stars, and they're, here's a typical sort of cartoon of one that has a radius of about 10 kilometers, mass about 1.5 times the mass of the sun. It's shown here as some sort of, in the center, having twice the nuclear density, and outside they've got a thin shell. This is a density of about 1 billion tons per cubic centimeter. In the center here, the picture says quark gluon plasma ? As if you compress nuclei so much that all the neutrons there meld together, they lose their boundaries and become a plasma of quarks and gluons. But a long time ago, I said it's too much of a mouthful, so I'll shorten it to quagma, which never quite took off because people think it's like quagmire or a horrible messy thing, but it's in the dictionary, so I got a word in the dictionary there. So anyway, neutron stars could be, I mean, they're there, but we don't think they're dominating the dark matter content. So the story moves on. There's now the cosmic microwave background. You see here, there's a whole sky map in microwaves, and it's basically microwaves with a thermal spectrum as a black body with a temperature of about 2.7 Kelvin. But what you see here is tiny variations at the level of 1 in 1,000 or less, actually 18 millionths of a Kelvin, microkelvins, where it's slightly hotter in places and slightly colder in places, slightly denser here, slightly less dense there. And the idea is that these probably resulted from quantum fluctuations at the Big Bang, a long time before the microwaves were emitted here, and could be the origin of structure in the universe, making galaxies and so on, where the denser parts condense more to become stars and galaxies by the mutual gravitational attraction. Now, studying the sky map, you can see there's all different scales of fluctuations. Some are very, very small scale fluctuations, some are larger scale, and you can quantitatively measure by sort of Fourier analysis the size of these fluctuations and plot them on a graph here with large angular scale on the left-hand side. 2 is a dipole where the whole sky is hotter on one side than the other. Actually, you have to correct for the motion of our microwave telescopes through the galaxy. Small angular scale up here, and you see the points are the data from analyzing these maps, and the curve is a theoretical prediction from what's called the standard model of cosmology, and it is made to fit extraordinarily well. I mean, it's just amazing how well it fits, except here on this big scale, which is a bit messy. But that standard model has something like only about 5% of the stuff in the universe is known matter, and about 25% is unknown or is dark matter. And then there's like 70% left over, which is called dark energy, which is more mysterious than anything else. Next slide shows about dark energy. We don't know what it is, but we can measure it. It's causing the universe to expand faster and faster. So here's a cartoon of the universe history with time going up vertically. We're about 13.7 billion years since the Big Bang, where the universe apparently supposedly started out trillions of times smaller than a proton and expanded exponentially until it got to about the size of an orange, and then a phase transition happened, it heated up. That was the Big Bang. And then helium was produced, then hydrogen, and so about a bit of lithium. But all the matter we know, like, from carbon, nitrogen, oxygen, all our stuff comes from the stars exploding later on. Anyway, the relic radiation here is the map of the microwave background we saw. That's from when the universe became transparent, when protons and electrons found each other and became neutral hydrogen. That let light pass through, and the light has now become microwaves as the universe expands faster and faster. Now, this is, I say we don't know what it is. Einstein put a number in a term in his equation for the size of the universe, describing the universe. And he put that term in there because he thought the universe was actually stable. This was before Hubble said it was actually expanding. And he put a term in there to keep it stable and static and not expanding. And he said later that was his greatest blunder when he realized it actually was expanding. And now these physicists found that from the very distant galaxies, redshifts, that it seems to be expanding faster and faster, exponentially growing. Is that going to go on forever and ever, amen, or what? And we don't know what it is. But now there's a dark energy survey at Fermilab measuring the redshift of millions of galaxies. They've just published a new catalog. We don't know if it's constant in time, if it's uniform in space. We're sort of assuming it is, but it could possibly be changing with time, and even non-uniform in space. I mean, it could be denser in patches. We don't know that yet. But most theorists think that it's just uniform in space and time. And even as the universe expands, its density does not go down as you might think it would. Okay, so that's all I have to say about dark energy, except I have an idea about them that I won't share. Now, now I have to change my slide. It's not changing for some reason. Oh gosh, it changed all at once many times. Okay, all right. So that's the sort of cartoon of the universe, time. So what is the universe made of? So what we think now is about 3/4 of it is dark energy in terms of the total energy content of the universe, and we don't know what that is. The dark matter, dunkle matière, from Zwicky and Rubin, is about 21%. And normal matter that we know and love and understand, we think, is only about 4 or 5%. There's a mandala here of the standard model particles that we know about. So that's this 4 or 5% that we know. And it's quite a clever little diagram here. Put the Higgs boson in the middle. That's the only particle, fundamental particle with no spin at all that was discovered at the Large Hadron Collider. The next circle in blue, photon, gluon, W and Z bosons. These are the spin 1 particles that transmit forces, electromagnetism, the weak force and the strong force. And they've all got particles got spin 1 spin. And then outside the circle is the particles of matter called fermions. They've got spin 1/2. In the top half, you see the quarks, up, charm, strange, down. They only the up and down quarks are stable enough. They form protons and neutrons. The others are all unstable and decay very quickly. So they're not really much part of the matter. At the bottom, we've got the green ones, which are particles, again, spin 1/2, but matter particles, but they don't feel a strong force. They only feel the electromagnetic and weak forces. Well, these tau, mu, and electron are charged and they feel electromagnetic and weak. The 3 types of neutrinos don't even have charges. They only feel the weak force, but those stable in red. And then, so the others are all decay. Now, there's another on the next slide, which is sort of an old slide from a talk I gave before, is another diagram here of the fundamental matter particles. On the left, you see the quarks, the orange ones, 6 of them. The up and down quarks, U and D, form protons and neutrons and make us. That's not United States, it's us, with the electron orbiting around it. And then there's the 3 types of neutrinos at the bottom here that have no strong charge, no electromagnetic charge, only weak charge. And they are definitely part of dark matter, but they seem to be only a tiny part of it, as far as we know. And these other particles, charm, top, bottom, which were discovered at Fermilab, the tau neutrino was discovered at Fermilab, and these others, they are making up this pattern that we don't fully understand. And then the force particles here and the Higgs boson there. So, all right. So I say all normal matter, proton is up, up and down together. Neutron is up, down, down together with electrons going around, and neutrinos are weird. So dark matter particles, assuming they're particles, they probably have no strong electromagnetic or weak charges. At least to our normal matter particles, they're invisible. But I can't read underneath my screen share anything. What did I say there? But portals to these particles may exist. That is, some particles that we haven't yet discovered that do connect with matter particles that we know and love to dark matter particles that may be just hidden. They're in a sort of hidden valley, if you like. That's a term people are using now. So these are new particles that couple to standard model particles, the ones I showed in the diagram before, and dark matter particles. which could have a complicated spectrum themselves. There could be many different types of dark matter particles, like there are many different types of matter particles, but the coupling is weak. Question, can we find dark matter particles or these portals at this Large Hadron Collider at CERN? And here's a beautiful picture of CMS, the compact muon solenoid at the Large Hadron Collider, that I'm privileged to be part of with a few thousand other physicists. And here's a person you see. It's a huge thing. You see it opened up, actually, that's half of it. The other half is coming in. So it's a massive enterprise and really exciting to be part of that. And we've been looking in data from here for new particles and not finding any so far. So apart from the Higgs boson, of course, which is part of the standard model. So are they these weakly interacting massive particles or WIMPs? They could be very massive and needing the Large Hadron Collider or even a higher energy collider to produce them. You remember E is mc squared. A higher mass particle needs more energy to create it. But searchers at the LHC not finding them so far. So now there's a lot of, maybe they're too heavy for the LHC, but they could be light, just interacting very weakly. And so we haven't found them yet, but difficult to find. Sort of like neutrinos, but not neutrinos. Something more than neutrinos is needed. And I listed here several different types that people are thinking about. Thing called dark photons. They're like photons. They've got the same spin. They're much like photons, except they couple to charge very much less than photons do. Any particle that produces photons is going to produce these dark photons, but maybe only 1 in a million or 1 in 10 million or whatever of them will be dark photons. We don't know what the mass might have, but they may have a mass of like the proton mass or 10 times the proton mass. Then people talk about a possible dark Higgs boson, like the well-known Higgs boson, which got this heavy mass of 125 GeV. That's like 125 times the mass of proton. Dark Higgs would have spin 0 like the Higgs, but be much lighter and maybe not, and we haven't seen it yet. Or another class is heavy neutral leptons that about like neutrinos. They got the same spin as neutrinos. That's 1/2 a unit of spin, like the quarks have and like electrons have, but a weak coupling, but heavier than neutrinos. Maybe, mass of GeV or 10 GeV. We don't know. And there's a fourth class called axion-like particles that have spin 0 also, but this is to do with CP violation, that is the matter-antimatter asymmetry in the universe. Now, I just can't, excuse me, when I share my baby, my project that I'm working on, which is hopefully going to discover these particles. It's not yet approved and data wouldn't come before 2028, but here's a sketch of the apparatus. The collisions happen 100 meters up to the left here. And these dark particles could come through 50 meters of iron, additional shielding, and then not be seen in a counter hodoscope here, an array of counters, to not see it because it's neutral and it comes into the pipe where I have a big decay volume, 18 meters long and 1 meter diameter, and look for it decaying to 2 or 4 particles in this vacuum pipe, and then have a set of detectors on the right-hand side to measure these particles very precisely. And if we see something that comes through all this shielding and then decays, it couldn't be anything we know because neutrinos come through, but they don't decay. And all the other particles don't get through. So that's what's, and here on the left is a calculation by some theorists. If there were heavy neutral leptons, and on the left hand, you see the scale here from 5 GeV mass up to 30 GeV mass. And here's the strength of the coupling between these particles and the muon. And the pink boundary is what we could search for in this project compared with other projects that are not approved yet either, except this one that is approved but is not so sensitive. So there. And there's a lot of experiments now searching for these dark photons. Here's a complicated picture, again, of the mass scale on the left, up to 1 GeV or more, and the coupling strength here on a log scale. That's like 1% of normal electromagnetic coupling down to 10 to the minus 5. And different experiments are searching in different regions. And the search region I'm after is down here, higher masses. If there's something there, we could find it, which would be exciting. I'll tell you in 10 years' time. I thought people might ask about G-2. So here's an older slide also before the latest news about that, showing the muon ring where muons are stored and circle round and round and round the ring, wobbling in the field, and you measure the wobble, wobble, wobble over many, many cycles and calculate the magnetic strength of the muon. And we did remeasure it from after it was done at Brookhaven, confirmed the difference from theory. And now this is theoretically because the muon's not an isolated particle, but it's surrounded by a vacuum, and the vacuum's full of virtual particles. And the calculations, the difference between the calculated value from theory and the measured value is now stronger. It's 4 standard deviations. And this suggests that maybe unknown particles in the halo or vacuum around the muon that are missing from the standard model. Or it could be some subtlety in the very complex calculations that we have not understood yet. So the jury is still a bit out. So finally, or nearly finally, I couldn't resist showing this picture of the world. This is the Isle of Quarks with up, down, strange charm, bottom and top. This is the Isle of the leptons with neutrinos and taus and atoms up here and so on. And then here's the Higgs here, antimatter, blah, blah, blah. And unknown territory, these crazy animals out there, dragons, etc. Extra dimensions, all the crazy ideas that theorists think about. So here's my last slide. I'll leave you to read Dilbert, and thank you. So I didn't allow time for any interruptions or questions, but now we've got time for that. So there you go. Thank you.
Yeah, we certainly do. Thank you very much, Mike.
Yay!
So a question came to my mind when you were showing the cosmic microwave background and how the structure of the deviations in the temperature correspond to the standard cosmological model, the predictions that come out of that. And my question is, does that predicted profile require or presume weakly interactive massive particles? Or, you know, you said that dark matter is something that contributes to that profile, but do they presume that dark matter does do some weak interactions in order to generate that profile, or is it just gravity?
I'm going to ask that to John or Ivan. My quick answer is that it doesn't say that the dark matter has, it says that it's there and has got mass, so it interacts gravitationally, but it doesn't say that they've got weak interactions. I think that's the answer. Do you agree, John or Ivan?
Indeed, the weak just means not strong. It doesn't refer to the electroweak interaction.
So this shows that there's stuff there, presumably particles, that has gravity. So, but it doesn't say, I mean, it could be that it doesn't have any normal weak interactions, what we would call weak interactions by the W and Z boson. And it could have no connection, so there could be a sort of parallel world out there of particles that interact among themselves with their own sort of strong force, but they don't interact with our particles at all, except through these possible portals that we could find, these particles that do interact both with dark matter particles and with our standard model particles.
There's no requirement that the portals exist. It could be that there are parallel worlds of particles that interact with our world only through gravity.
Yeah. In case we'll never discover those particles, I think. We can just say, well, there's mass there, but we would not be able to discover the particles they're made of. Yeah.
I have a question about this idea that Sagittarius, the object near Sagittarius A, is not a black hole, or at least is made of dark matter. I assume that even if it's made of dark matter, it might still be a black hole, right? But maybe it's a different kind of degeneracy. Is that the idea?
Yeah, I think, yes, right. So a big lump, a massive lump of dark matter would form a black hole and would be indistinguishable from a black hole made of matter. I think these astronomers are saying that the signs you would expect from this supermassive black hole in terms of other radiation from it are not apparently there. So maybe it is not actually a black hole, but just a very massive object that's not, I don't know, gobbling up stars and radiating. I haven't seen the paper. In fact, to be honest, I only heard about this idea today, and it was in a talk by Dr. Becky, who does a very nice, actually, podcasts She's an astrophysicist in the UK, and worth checking out, Dr. Becky. She mentioned it. I haven't seen the paper, so I don't know. But
Well, there's a result or a set of results that I've actually been involved in where we showed that Sagittarius star has what's called an advection-dominated accretion flow, where the energy released by the accretion actually disappears from the universe.
Really?
Which suggests that it falls down the black hole.
That's
Okay.
amazing. Really, I hadn't heard of that.
It's Google ADAF. Yeah.
could
So
you,
what happens is that if the accretion flow has sufficiently low angular momentum and is sufficiently slow, it doesn't form an accretion disk. It can just fall into the black hole, and it doesn't get hot and it doesn't radiate, and all the energy winds up in the hole and none of it re-radiates into the universe.
So the energy just vanishes. The radiative.
Well, I mean, it adds to the mass of the black hole. But it doesn't show up as radiated energy. Sagittarius A star is a very weak X-ray source. It's not radiating very much.
John, can you explain better why these guys think it may be dark matter rather than normal matter?
Well, of course, you can make a black hole out of anything. You can make a black hole by colliding gravitational waves.
But still, to say they think it's dark matter, they have to have some reason for saying.
I have no idea what the result is.
It sounds very iffy.
Well, no.
Yeah.
We don't know where these supermassive black holes in the cores of galaxies come from.
Right.
One hypothesis that I've seen recently is they get their seeds very early in the universe from collapse of dark matter clouds. Which is possible because we don't know what the dynamics of dark matter would be, in the very early universe. But it's all speculative. Yeah. Oh, one nit. The two in your cosmic microwave background fluctuation spectrum refers to two cycles around the sky. So in fact, it's the quadrupole term, not the dipole term. The dipole term doesn't belong in that spectrum because the only way that we can measure our motion relative to the rest of the matter in the universe is by looking at the cosmic microwave background. There's no way to add up all the contributions of the motion through the galaxy and the motion of the galaxy in the local group, et cetera, et cetera, et cetera, to do that correction for the dipole.
Well, can I turn that around? Because I agree. So they take out this dipole, which they say, okay, we've got that because the motion of us, our planet, through the microwave background, right? But then we know the motion of the Earth around the sun, the rotation of the telescope.
Yeah.
So if you add all that up, how well does it agree? I mean, or is there a big?
Oh, hundreds of kilometers per second difference.
What percentage is that?
Well, the Earth, the motion of the Earth around the sun is 30 kilometers per second.
Yeah,
and
then
the motion of the sun around the galaxy is comparable to that number, but the vector is different.
Right. So if you add up everything that we know about the motion of the Earth through space, and compare it with the dipole that they observe.
Oh, it's hundreds of kilometers per second different.
I just want to say you may wish to simplify what you just said, viewers.
Yeah, our viewers probably aren't. Our viewers probably aren't aware.
Like, yeah. So the general idea is that long ago the universe was very hot, and it was like the inside of a fluorescent tube. It was a plasma, and it was opaque, and it was in thermal equilibrium, and that when the universe cooled, the light from that spread out and is that we can still observe it today, but the spectrum is now shifted, so it has it's much lower apparent temperature to us, And because it was going in every direction, we think that this radiation should be, I'm going to completely botch the way of saying this, but in a sense, it defines a frame. It defines like a almost like a rest frame in the universe.
Yeah.
And so when we look at this radiation everywhere, if we want to know how fast are we moving relative to this special frame, we can look at that spectrum, average it, and then say, okay, if we were moving in this direction with this speed, then this average would be symmetric in every direction.
So that's the Doppler shift, right? The Doppler shift due to our motion.
Yeah. And that when they show these plots, they take that out, they subtract that out. They say
That's right. When they show the sky map,
yeah,
you take the dipole out.
Yeah.
But when you show the spectrum that you showed,
yeah,
the 2 on that spectrum is not the dipole. The 2 on that spectrum is the quadrupole.
Oh, okay. Well, that's technical. Okay. Yeah, right. Very technical.
And one of the great mysteries is that it's like 2.5 sigma off the prediction. And the trouble is that you really can't do anything about that, because you would have to redo the experiment of having another big bang and seeing whether it was still depressed relative to what we expected.
All right, now you're working on that, aren't you, John?
Well, I have a question for you about that, because that sky map did not show the Milky Way, but we got to look through that. So there must be this foreground Milky Way. It must be an annoying problem there. So,
oh yeah. I'm not sure which sky map. There are lots of sky maps, and it may have been interpolated through the Milky Way, or it may, I don't know. Yeah, there are many wavelengths that you can do this at, and and the Milky Way shows up differently at them, and there are various ways of working on that data, and I don't know specifically what was done to remove the Milky Way from that map. Traditionally, that map is plotted with the plane of the Milky Way going straight across the middle.
Yeah, right. I'm not seeing any sign of it.
Yeah, I'm not exactly sure what is being plotted there.
Well, what is the temperature map?
It's not simply the bolometric flux, because then if you did that, the Milky Way would stand out. So there's some data processing that was done on that map to remove the Milky Way, using the fact that its spectrum is different and things like that. But I'm not quite sure what it is.
We've got a couple of questions. We've got one question online, actually from Dave. He said, if we've got 2 or maybe 3 different species of matter, and he's defining that as matter, antimatter, and dark matter, what's to say that there aren't 4 or 5 or 10 to the 30th different sorts of matter in the universe? And
there is absolutely nothing.
Okay.
Oh, good. That narrows it right down.
We simply don't know. We have knowledge of matter that we are made of, and of additional quantum fields that interact with the matter we're made of. Yes, and then that's basically it, except for these observations of the gravity of something. But that something doesn't need to be a singular quantum field. It might indeed be 10 to the 30th different kinds.
Cool. Thank you, John. Peter, you had a question?
Yes. harking back to Joanne's partially humorous question to John about working on the Big Bang regeneration. John, I'm wondering if you know of, in the supercomputing world, are there any low parameter simulations, meaning obviously with the limitations of our knowledge, are there any kind of low parameter simulations of the Big Bang?
Yes, and that is where the line on the plot that Michael showed, the fluctuation spectrum, comes from. It comes from simulations of the Big Bang.
Okay.
And of course, when you do many simulations, you can get a very small spread of the mean, and so you can make a nice narrow line, and then you only get one chance of measuring the universe, and so the observations fluctuate around that line according to expected. The error bars, I believe, come from the theoretical uncertainty from those simulations. So yeah, we can simulate.
Yeah.
Okay.
An interesting point,
I-
by the way, about the simulations is that even before the smoking gun for dark energy, the thing that Einstein called his greatest mistake, with the type 1a supernovae results, once we got the type 1a's calibrated as distance indicators, back in the 1980s, people were doing simulations of clustering of galaxies in the universe using supercomputers. And the interesting thing was that you throw in matter and you throw in dark matter, and then you stir the pot and you run it, and you see patterns of galaxies, and they didn't match until you threw in dark energy. And so there was a hint of this from simulations of the universe even before it was solidly detected using the accelerated expansion as measured with type 1a supernovae.
Just to be clear, this picture is not a picture of the Big Bang. It's a picture of the universe as it was when it became transparent to photons about 30,000 years after the Big Bang. But the idea is the Big Bang was absolutely perfect.
Yeah, I didn't assume.
Yeah.
380,000 years, I believe.
Sorry.
It's a picture of the surface of the two-dimensional surface of the three-dimensional problem that is currently visible to us today. Because what happens is that as you as the universe ages, maybe I'm wrong. This is, we were once part of that plasma that is visible in that plot. And so what we're seeing now is the plasma from a different part of the universe that
At a different
the
time.
age that in its own frame is the age that we were when we were part of it, but because it's 14 billion, its light has spent 14 billion years getting here, we see what it was like back then.
Well, yeah.
But
Right.
you would expect this.
Yeah,
You would
it's
expect this.
distorted, right?
You would expect this to evolve. There's not just one of these because it's a two-dimensional surface, but the universe is three-dimensional.
Well, it shows the surface of last. Anyway, what I'm interested to see is you can see here you can see my arrow. Where's my arrow gone? South America, and you see a ring of fire around here. I mean, isn't it nice that the eye is so good at seeing
Very
patterns and
lovely.
things?
Oh yeah.
This always looks
Australia
like
out
South
here.
America.
Oh, yeah.
A line of volcanoes here and another line of volcanoes around it, you know.
So that
Yeah.
reminds
interesting.
me that reminds me of a phenomena called self-similarity in fractals. So if you look at a fractal at nearly any scale, depending on the fractal, you can see this sort of similar features at many different scales. But in this case, Mike, you're just jesting, right? There is no correlation between the CMB and
Oh,
the
darn.
continents of Earth.
It is an interesting point, though, that this really isn't a fractal, and it's this spectrum that you see on the lower right that shows you it isn't a fractal. Because if it was a fractal, the spectrum would just be a log linear line, a log line, I should say, a straight line in a log plot.
Right.
And this has all sorts of bumps and wiggles, so it's not a fractal; it's its own thing.
And another interesting thing about this plot that I love, kind of going off on 2 minutes of a tangent, is that current theorizing holds that the reason there is a little bit of discrepancy from place to place in the early plasma of the universe, the reason there are tiny little hot spots and tiny little cool spots, is related to the fact of quantum mechanics. So if you roll the story of the universe back to the hot origins of the Big Bang, you have to start thinking about quantum mechanics, and specifically quantum uncertainty that allows for slight random temperature fluctuations that have no other cause. They just exist.
Yeah.
To me, the most remarkable thing about this is that this is from the mission WMAP, the space mission. And before WMAP, I went to a colloquium where one of the theorists working with the WMAP project presented the plot that is on the bottom right. And he said, here's what we're expecting to see. And it was all those bumps and wiggles and all that. And I thought, you're crazy. It's gonna be something, but it's not gonna be what you expect. But the theorists got it right. It's
so if
very impressive.
If the structures are resulting from quantum fluctuations, I asked an astronaut, if they're to do with quantum fluctuation, you should be able to derive. It should depend on Planck's constant, h bar, right? If you can derive Planck's constant from this data, then I'll believe it. Then I'll believe it. He said, oh well, you know, you're joking. He said we can't possibly do that. It's all washed out. But anyway, you know, if it wasn't for these fluctuations, then presumably galaxies and stars would not have formed. And another thing I was going to comment on. Suppose there's this parallel world of matter that doesn't interact with our matter at all, but does with itself. So you might have these dark stars and dark planets and so on. Well, there can't be too many of them, because if they were flying around, some would come through our solar system, disrupt the orbits of planets, which we've measured so very well. We could even put a limit on, I think probably people have put a limit on the number of dark objects flying through our solar system and disrupting the orbits of the planets. I don't know if maybe Ivan, you know, if somebody's done that actually, and put a limit on the number of.
The thing about that is that it's not that those limits are not very compelling, and we used to joke that the dark matter could be baseballs. But the problem is that the nucleosynthesis calculations for the universe have gotten much more sophisticated, and there's just not room to make condensable matter out of all the hydrogen and helium that you know, starting from hydrogen and helium, there's not really any way that you can twist all the models around so that they can make condensable ordinary matter out of hydrogen and helium of the Big Bang in the quantity that you'd need for it to be dark matter.
No, no, those dark planets would not be made of hydrogen or helium because that's matter. They would be made out of condensation of dark.
Oh, I see what you're saying. But in fact, the actual density of dark matter is extremely low. It's spread out in halos around galaxies. There was a lovely XKCD last year where they're talking and somebody says, well, the quantity of dark matter in the Earth is about equal to one squirrel. And the person that he's talking to says, oh, let's go find that squirrel and discover dark matter.
No, but that's assuming it's diffuse. If it's clumpy, then I mean, the density of matter in the solar system is very low, but it's clumpy planets. So maybe
well, but then if it's clumpy, the rate at which these things pass through the solar system is extremely low, and we wouldn't, if it's clumpy enough that you would see them as local gravitational perturbations, then we wouldn't expect to be seeing them in the solar system because the total density is very low. Now, one thing it could be is it could be primordial black holes of a fairly large range of masses.
So if we think there's like 5 times more, 4 or 5 times more dark matter than regular matter. So if our galaxy was, let's suppose there was no dark matter, but there was instead, we transform all of that dark matter into regular matter. To what extent would we expect our solar system to be stable, right? Like, in other words, and you can probably even look at a more dense galaxy and answer this question, like, do solar systems survive?
Oh, well, go back to Vera Rubin's plot, and you can see that the expected rotation from the visible disk isn't all that different from the rotation rate measured until you get outside of the visible disk. And so we're in the visible disk. We are in a part of the galaxy where the non-dark matter is dominant. The dark matter is a big halo around the whole system. And we're in a spiral galaxy where most of the matter is collected in a plane, and most of the matter, the visible matter, is collected toward the center. And the dark matter is not in the plane, and it's much more diffuse.
So there was a news story I saw today. I didn't get very far with it because I saw it just before the show, but about some galaxies that seem to be devoid of dark matter, which is an interesting scenario. I actually wanted to get back to Dave's question a little bit, which is like, so we have matter, we have antimatter, we have dark matter. Why can't there be 1,000 different things? Well, really, those classes are defined by, matter and antimatter is defined because of relativistic quantum field theory. But the reason that we don't say there's dark matter and then dark matter 2 and dark matter 3 is that really dark matter versus normal matter is a distinction based on visibility. Can we see it? So in the dark matter, what we've been talking about a little bit, or alluding to at least, is that among dark matter, there might be another whole bunch of particles which are dark matter particles, and maybe they have their own interactions which we can't see.
Yeah, right.
One of the things that comes up,
and they can be, as Dave alluded to, more than one class. I wouldn't say thousands of classes, but dark matter, that it could be, there's a whole class of dark matter particles that interact with each other, but not really with us. And then another class that doesn't interact with either us or the, so there could be more than one story there. That's going to be mean,
If we can't see them, the entire argument is sort of moot, isn't it?
it's sort of moot if you can't see it. Yeah. But
Well, there is well, one thing that's interesting, right, is that I know there have been discussions about, we think that if there was just like one weakly interacting massive particle, then those particles might have difficulty cooling off and condensing, right? Because what do they have to give their energy to something, and if they're not interacting with anything except gravitationally, it's hard to condense them, right?
unless they interact with each other.
Right. If there are
Strong-
different kinds of weak, or dark matter, and in their universe, they can radiate their energy away, then they might be able to condense. And so even though we can't see them, if we can say that, hey, these dark matter things can be pretty compact objects, that we already might know something about the physics of the dark realm.
Mike, can you stop sharing your slide so that the Zoom shows us talking instead of
Do that.
just stop sharing? Yeah, there you go.
Stop sharing. Right.
Yeah, so there's this notion of the dark universe that entails dark matter and dark energy and all their possible interactions. But one of the things that I believe I've learned, I could be mistaken, of course. One of the things I believe I've learned is that there is some evidence that dark matter does not interact with itself in anything analogous to the way regular matter interacts with itself. For example, regular matter can cool down because of friction. And when you really get down to brass tacks, friction involves matter emitting photons, so it gets rid of some of its energy of motion and converts it into infrared light or other forms of light. So you can slow down the motion of regular matter by having it interact via the electromagnetic force. And as I understand it, studies of the calculated distribution of dark matter within the halos around galaxies and in galactic clusters provide some evidence that dark matter doesn't have a way of dissipating its energy analogous to the way regular matter does. So it may continue to be just sort of isolated. The particles don't form molecules of dark matter. They don't form dark matter planets, etc. What do you guys think about that?
Yeah,
I don't-
that's kind of what we currently, that's kind of our model. That
I don't know. We have really evidence for that, do we? I mean, is it diffuse or is it clumpy? I don't know that. John,
It is.
one with the
It's
other?
clumpy on large scales, but I think that you might be able to put a constraint on it by saying, well, if it was a mirror, if it was a dark mirror of our own physics, then you'd expect to have just entire compact dark matter galaxies floating around, and we probably see those.
yeah, that's
Just
right.
because they would warp the light as the light comes through.
That's correct.
Well, another thing, you have looked for something like a dark star made of dark matter. If it moves in front of a normal visible star, then it bends the light, and you see that. You can see that people have been looking for that, for these events where something of compact mass moves in front of a star, and they haven't seen anything, I think, right?
Well, I've seen a few, but they're not enough to.
And to your point,
Be excited
originally,
about.
Mike, that's a good reason to not call it or not think of it as dark matter, because you might think dark matter would absorb the light of a star behind it. It's not dark matter, it's literally invisible matter.
Exactly, it is invisible matter. I'm sorry, dark matter got stuck.
Yeah, the words themselves are confusing. They just,
One other point I would bring up, I'm surprised that you didn't bring it up in your talk, Mike, and that is that there is a puzzle in the standard model that may lead to your portal, and that is neutrino masses, because we don't know where those come from, and those suggest there's an interaction we don't know about.
Yeah, I mean, there's a whole story, neutrino masses, and in fact, that's a major
item of research at Fermilab now, is understanding them, because there are three, I mentioned three neutrino types, one electron, one muon, one tau, but they're three different masses, and they're not the same things, they're mixtures of each other. And one idea is that there's a called a seesaw mechanism, where the neutrino masses come from very heavy leptons, and these things could be hugely heavy, but it could be that there are heavy neutral leptons that I mentioned, which are actually 10 or 20 GeV, and if they exist and got the right mass and properties, then I could detect them in my machine. So you know, that would be very exciting. But yeah, I mean, yeah, that's right, and yeah.
The sterile neutrino is another sort of exotic candidate.
Yeah.
And one of the other things that I think I've learned, hopefully correctly, is that one of the reasons that many theorists think that dark matter may be weakly interactive massive particles is because the weak force is largely responsible for all transitions from one sort of material into another sort. So when you have a proton that decays, I'm sorry, a neutron decays into a proton, an electron, and an electron anti-neutrino, or you have other particles that change sort of their species or their particle type, that's always implicating the weak force.
Yeah.
So my understanding is that the weak force will, in theoretical models, the weak force is implicated in generating particles from energy of any sort, even dark matter particles. So they might therefore be expected to respond to or interact with the weak nuclear force.
Now, the weak force carriers, the W and Z bosons, which are heavier than the Higgs, but the Higgs mechanism gives mass to those particles. And the Higgs is like a quantum of the vacuum. So the question is, does the Higgs interact with dark matter particles? And so CERN, they're measuring the different decay modes of the Higgs to see if they can account for all the decay modes with standard model particles, or is there something missing? Because maybe 5% of the time the Higgs decays to dark matter particles or portals or something like that. So, you know, we are accounting for many of the Higgs decay modes, but we haven't got everything yet. And there could be some, the Higgs can interact with dark matter particles. We haven't seen that yet, but it could be there at some level. Right. And
All
again,
right. Well, we are.
Go ahead.
Oh, go ahead, Mike. Finish your thought before I wrap us up.
My thought was, you know, there could be another Higgs boson that is lighter than the one we've seen, and that mixes with it, you know, and that's that could be even 10 or 20 GeV. Another possibility for me to find it, if I'm lucky. If God.
All right. Well, good luck.
Thank you.
Good luck to you. Good luck to your experiment. Good luck to all the physicists out there trying to crack some of these remaining puzzles. You know, we've gotten to protons, neutrons, and electrons, and for a lot of folks, for a lot of time, we thought we'd got it figured out. But the particle zoo surprising us, and now cosmology has surprised us with dark matter and dark energy, about which we know almost nothing. So with that, I think we'll wrap it up for this week. We'll be back in a couple of weeks, and thank you for tuning in and for joining us, and have a great holiday weekend. We'll be back on July 10th after the holiday weekend for Independence Day. So take care. Oh, happy June.
Juneteenth.
Juneteenth, everybody. Brand new holiday.
Happy
All right.
undiscovered country.
Right.
Happy undiscovered country.
Yes, indeed.
Okay.
All right. Thank you. Take care.
Take care.
Have a good one, everybody.